And the first speaker is going to be Gergő, and he's going to be telling us how to use Clash to implement a FPGA for solving Sudoku puzzles. Gergő, please.
Yeah, thanks. So yeah, so this is a function of Perl, which I'd like to point out because there's not necessarily that much science in this. There's a big part of it is just neat, but I think it is neat, so I think it's worth sharing. So okay, so what is it? What are the various pieces of things that we're going to be talking about? So I'm going to very briefly introduce Sudoku, which is a combinatorial puzzle. And then there's a 2006 function of Perl by Richard Bird, where he derives a Sudoku solver written in Haskell, like a normal software Sudoku solver. And yeah, he derives it in his usual way of starting from a specification and applying and writing a really naive and horribly performing version, and then applying a succession of program transformations to it to get something that performs well. Is very nice, like reading it is nice, and the way you get there is also very understandable via these steps. And then what I'm going to do is I'm going to translate that onto something that runs on an FPGA. And the tool I'm going to use for this is Clash, which is a Haskell to FPGA compiler that takes Haskell programs and compiles it to FPGA configuration. So it's going to be, yeah, like a putting together all these things. And if that sounds familiar, that's probably because you were here on Monday and you heard Satnam's keynote, because I think this matches very closely the aesthetics of the approach that he was advocating for hardware design. And I also hope that you went to that meetup, because I think I can use that to skip over maybe some of the introductory stuff. Okay, so Sudoku is a combinatorial puzzle game where you're given a grid like the one on the left-hand side. In this case, it's a 3-3 Sudoku. So you have a 9x9 grid, and you see that it's divided into rows, columns, and 3x3 boxes. And you want to fill in the missing, like the empty squares, such that the digits 1 to 9 appear exactly once in every row, column, and box. And so on the right-hand side, you have a solution for this. So it's like your goal is to go from that to that. And like there is not necessarily a unique solution, but let's see if we can solve one. And just a small thing. So we can generalize this. You can generalize the Sudoku by its size. But and people normally think that the standard Sudoku is like the 9x9 Sudoku, but that's actually not a very precise definition, because these two are both 12x12 Sudokus, but they have very different constraint structure. So it's a 3-4 Sudoku, because you can see that you have 3x4, you have a 4x3 matrix of 3x4 boxes, and here we have a 2x6 matrix of 6x2 boxes. So even though the sizes are the same, they have different constraint structure, because this guy is a neighbor of this guy, whereas this guy is not a neighbor of this guy. They're not in conflict with each other. Okay, so we're going to solve this problem, and we're going to solve it using Clash. So what is Clash in its essence? So the usual way of describing synchronous digital circuits is this so-called register transfer level abstraction. So you have a bunch of these registers, and they are clogged, hence the synchronous part. And you have feedback loops via these registers. So they are connected to each other and connected to themselves. Like you can see that the value of the register that comes out, the Y, feeds back into some combination of circuits. So this imagine that it's just like a network of stateless circuits. And then it also has inputs from other registers like the X, or maybe it's an input from the outside world, and then Y might feed into an output from the outside world. So you have a network of these, and that's basically what you want to describe when you're working at the RTL abstraction. And so what Clash gives you is it is this. Like anything else just follows from the fact that there is a type constructor called signal. It is indexed by the clock domain so that you can't accidentally connect two registers that run at different clocks, because you really don't want to do that without making sure that there's some meaningful synchronization happening there. And then you have register, which is a primitive that takes an initial value for every register, and then implements like this box, right? So it takes a signal of type A, and then whatever comes out of it will be at the next cycle is what you get as the output. And to be able to connect these registers, it's an applicative functor. So that means that the pure parts of the combinational parts of your circuit can be described as pure, and the connections themselves become applications. So as an example, like this network we see here, we can describe it saying that, okay, y is equal to a register that starts at some value, let's say 19, and then it's updated in every cycle to the result of applying fun, which would be some pure function, applied on x, which is like some input from the rest of the circuit, and y is the thing we're defining. So this is recursive, right, in y, but note that the recursion is guarded by the register call, and that's the important part, because that's why it describes this circuit instead of describing some not really meaningful circuit where you have a direct feedback line. And also, yes, you can see, sorry, just one more thing. So you can see that its type is unsigned 5, which means it's a 5-bit wide unsigned number. And this might sound exotic if you're used to software, like a 5-bit, we don't have 5-bit values. But of course, if you're working with hardware, you have much more freedom on like the width of things, because at the end of the day, it really is just 5 parallel wires that you're gonna manipulate somewhat consistently, but it's still 5 signal lines. So why not have 5, just as easy as you can have 8 or 64? Okay, so that take care of the clash part. And as for our approach to solving Sudoku, so there's this function of Perl, and we're going to use a specific, so like it's a step of refinements, and we're going to use a specific step in that process from that paper, which is a classic backtracking algorithm. So you have an internal representation of the solver state, which consists of the candidate values for every cell. So you have your 9x9 grid, and then what are the values that are still possible for each of those cells. And then you do pruning, because if you know that a given cell can only be a given value, then you also know that all its neighbors can't possibly be that value. And you just keep doing this. Like you keep turning the crank, because when the result of pruning might be that a cell becomes a singleton, like a value that only has one possibility. So now that itself can help in pruning other neighbors. But at some point, you might run out of things to do. Like you get into a situation where there's no more pruning to do, and that's when the backtracking comes into play. So basically, you make a guess, and you just try solving the guess. And if that doesn't work, then you backtrack. So this is a slightly rewritten, reformulated version from the paper. But the details don't matter that much. The basic point is that given some Sudoku grid, we have a bunch of branches. We detect if we need to backtrack. We detect well, actually, so the backtracking is kind of implicit here, right? Because what we do is that when we are blocked, when we know that there's a conflict, we just return empty, like this runs in any alternative functor. And then when we need to guess, there's this expand function that gives us all possible guesses that are still consistent with what we know so far. And then we just take the alternative sum over trying all those directions. So this is software, right? This is not Clash code yet. And okay, so then we want to turn this into hardware. So the very first thing is that the circuit is going to be like a real circuit. It's going to have a fixed structure. So of course, it's not going to be polymorphic over all alternative functors. So we're just going to stick to maybe, which means that we're going to get the first, or like we're going to get one solution if there is a solution, and we're going to detect if there is no solution to the given Sudoku problem. By not having a solution, I just mean that the initial constraints were inconsistent. So the next step we need to do is to make sure that everything is using fixed size representations. So no lists. So the Clash standard library gives us length indexed vectors, And then we can, of course, use two levels of that. Like a vector of a vectors is a matrix, it's a 2D structure. And then to make it easy to track this structure, you know, like the 3-4 Sudoku versus 2-6 Sudoku, we're going to represent the grid as a matrix of matrices. So it really is a 3x4 matrix of 4x3 matrices of cells. And what is a cell? Well, I said that the internal state of the solver is all the possible values that are still valid for a given cell. So we're just going to use a bit vector of the right width to represent cells. And so now we can say that an NM Sudoku board is just an NM grid of n times m long bit vectors. So the main operation that we need to be able to do efficiently is pruning. Because like other than pruning, we're doing like guessing. And of course, the whole point of doing the pruning is so that we don't have to guess that much. Because, you know, like the stupidest possible solver you could imagine would be one that just tries guessing everything and hopes to eventually get. But that doesn't work for Sudoku. I mean, it's an exponential block, right? So you want to improve that by pruning. So we can implement pruning by representing masks separate from cells, for the very simple reason that we only want to include cells that have only a single possible value in masking. So we can turn a cell into a mask by saying, okay, is this a single value? If so, then the mask becomes the same bit string as, or bit vector as the cell itself. Otherwise, we want it to be neutral in some sense. We will get back, like you might say, okay, I'm using m empty here, but I haven't given a monoid instance to mask yet. So what's going on there? I will get to that in a minute. But just one thing I want to point out before that is, of course, we could compute the singleness of a cell from itself. Like there's no point in passing a Boolean telling us if the cell is a single bit or not. We could just check it. The reason we don't do this is because, as we will see, we're going to do it in many different contexts where we need this property. And we want to share that. We want to have a single piece of circuitry for every cell that, like, I don't want to say caches it, but, you know, like you want to share the circuit that computes whether a bit vector is just one, as just one bit. So how is bit mask, how is mask a monoid? Sorry, this should be mask, not bit mask, sorry. So the basic idea is that pruning itself is a monoidal action, because if you have the mask, if you have two masks, which are just bits, right? Just bit strings. So if you combine them using bitwise OR, that corresponds exactly to saying, okay, so this can't be, this bit is not valid, this bit is not valid. So if I combine them, both of these bits are not valid. These are not possible values anymore. And that, of course, also means that the empty case is one where you have no bit set, because that means there are no position or no bits where I know they can't be valid, because I don't know anything yet. And then the action itself is just removing the bits from the set of candidates that we already know can't possibly be values of that given cell. And so if you, like, okay, you might say, okay, this is formally not a monoidal action, because, like, what even is this bool? How does the bool come into play? But if you think of this morally, if you think of the bool as something that you could, in principle, compute here from the cell, then this would formally even be a monoidal action. But for us, really, all that matters here is that if you take the m-concat of masks and then you apply that on a cell, it really is the same as if you kept applying different masks. So the next thing we need is the constraint structure of Sudoku, right? Because so far everything has been on the cell level, but what we really want is for cells to communicate with each other via rows, columns, and boxes. And so what we can do for that is to say that, okay, any group consists of n times m cells, and then a full grouping is n times m groups. And if we do it as bidirectional functions, so like here you see that this A, B, both ways arrows just means you have a way of going from A to B and B to A. So if you use these two-way mappings, then what that gives you is that we can fold over groups by basically going into the grouping, so reshaping our grid into a vector of rows or a vector of columns or a vector of boxes, and then folding each individual such group, but then we can smear that back into the original structure. So I have a picture coming up just a second that should show this, but let me just quickly show what the code looks like. So basically we can say that if we have a grid of monoidal values, we can fold that via its three groups by folding it row-wise, group-wise, and box-wise, and then putting those three cell by cell, combining them using mconcat or mappend. So this is what is happening. So in this example, this is a 2-3 Sudoku, just so that it's small. So when we fold by rows, what that corresponds to is for every row, we take the monoidal combination of the masks, right? Like, so if I know that something has to be, like like this cell, right? It has to be 1. Like this is something that, for example, part of the original problem. Then in the first row, I know that nothing can be 1. So all of these cells, when you fold by rows, the mask that we compute from this, which is the one where the 1 bit is set, is going to be set everywhere. Because we first, and of course the 2, the 3, and the 4 as well. So when we combine these, we get 1, 2, 3, and 4. And then we smear it into the whole row. So now every cell in the row has the mask 1, 2, 3, 4. And the same happens for the columns, and the same happens for the boxes. And the reason we do it is because if you then look at this middle column, then if you put them together, so if you then like zip them basically, then for each cell, you're going to have both the cell that comes from all its horizontal neighbors and all the vertical neighbors and all the box neighbors, which is what you will get here. There's a slightly zoomed in version here. So we first fold by columns. Yes, we get the, so you see that every column now gets the same value, which is the combination of everything in that column. And then when we put it all back together, these three neighborhoods of every given cell combine to give us the mask of everything that can see that one cell. So yeah, and that is basically what pruning is, because then you just apply the monoidal action of these masks on the values that are there. And of course, remember that for values where we have only one candidate, masking or pruning doesn't do anything. That's the whole point, that we already know what those values are. Okay, so then the next thing we need to do is branching. So original software version returned a list of guesses. That is problematic because like a list is not good for us if we want hardware that actually manifests this structure. But you don't need to guess n way. It's enough to guess 2 ways if your second guess is something from which you can continue guessing further and further if you need to. So the way we do that is we can split every cell that is not a singleton. We can split it into its least bit, and that is set, and all the other bits. And why the least bit? Well, I can refer you back to an ICFP talk from Tuesday, I think, where Brent Jorge's Fenwick tree Perl showed in great detail why you can compute the least set bit of an n-length bit vector as just a negation and a bitwise end. So this is like super, super efficient to implement in hardware. And also note that once you remove the one bit, like the least bit, if what the rest is all 0, that exactly must mean that you only had 1 bit. So the reason that we were passing this is single as a parameter everywhere is because we can actually get that for free from here as well. Okay, so the next thing we need to look at is the fact that this is still recursive. And recursive, if you think of this as just really just putting it into hardware, that would mean you have like this infinitely big circuit, because every time it recurses, it will need a copy of itself. Of course, that's not what we want. What we really want is to have something that over time uses the same one copy of the circuit to make progress. Like in every cycle, you would do something by pushing things through the same circuit. So okay, so how is this recursive? Well, it's recursive two ways. It's both tail recursive and also non-tail recursive. So the tail recursive thing is very easy to imagine how to solve that. You really just need a register, and then the current state comes out of it, and you feed it back in by pushing it through the same circle. And for the non-tail recursive thing, what you really want is, so first of all, we make a pure function. This is still in the world of pure functions that does one step of this recursion. And then this is what we were going to do in a single cycle. And then we write some stuff around it that implements a stack of these. The second, like basically, when you guess and you branch two ways, the second one is the one you will push on the stack so that you can get back to it when you discover that you're blocked from further solving, because there's a conflict. And so here you can see a model of this using a Haskell list as the stack. But of course, this is not what you can do on hardware. So what you can do on hardware is you can use a piece of RAM to implement this stack. So we basically use a primitive from Clash, where given a memory command of n cells and data of type D, it will give us in the next cycle the read result of the previous cycle. And the stack frame itself is just a Sudoku board, right? Because the continuation is just something where the guess that I have already made is no longer valid because I came back here, I arrived back here because I realized that that guess is not going to work. And this also means that we know the stack size, I mean the limit on the stack size, because it can never be more than the size of the Sudoku board, because every time you guess, you make one of the cells into a singleton value, and we never touch those other than backtracking. So everything is nicely finite and fixed size. And that's basically it. And then there's the rest of it, which is like, the difference between, like in the software world, right, you write a function, but you also have to write main to make it into a program. So the rest of it is I/O. So this is a standalone device. So you load it onto your FPGA, and then you can communicate with it via serial link. And then you just basically connect either like your computer, or you take your 1970s terminal and plug it in. And then you just type in your Sudoku board, like you see here in the left-hand side. And there's some very fancy parsing going on, because basically we ignore everything that is not a digit or a dot. So this allows you to have this nice ASCII art. It's completely ignored. You don't need this. You could just type in the numbers after each other. But this is very nice because it allows you to copy-paste human-readable problems. And then what comes out of it is this thing that you can see that is nicely formatted. So this really is the output format with the extra spaces to emphasize the n times m times m times n structure of the board. So the whole thing hangs together by basically, we can do the same thing as software Haskell's interact function, which is like, so interact takes a string-to-string function and gives you an I/O unit, right? Where every line is pushed through that function and what comes out of it is printed. So using this library called Clash protocols, we can then compose our Sudoku solver plus the controller of it. So the controller here is the thing that handles the stack, basically. So this we can compose with the parser and the formatter. So the formatter includes also injecting these white spaces. So we can compose that, which you see here. And then we can we can actually write a general serialized combinator, which, just like interact, takes a circuit that produces and consumes bytes into something that produces and consumes a serial transmission line. And you can see, of course, that I'm using type application syntax here and here and here, just to emphasize that, first of all, this is the code itself is fully generic over the size of the board. But of course, we need to instantiate it to a given board size to produce a concrete hardware. So these two threes are just the fact that it's a 3-3 Sudoku. And then the speed of the serial link is 9,600 BPS. And that also has to be on the type level, because we do some type level computation to compute the clock divider for your FPGA to implement that specific speed. And of course, now with the recent enough GHCs, you can use the require type arguments extension so that you don't need the ats then, and it really just looks like a function application, even though that 9600 is a type level argument. And so that's basically it. So what is it that we achieved? So first of all, it turns out that it's super nice to use Clash for anything because the testing on the software side is really easy. Most of this stuff, like all this monoid stuff, that's on the pure side, right? So you can just test that as normal pure Haskell functions using whatever Haskell testing methodology you want. And Clash has a simulator which you can use to do the integration testing. So if you want to include all these other parts in your testing, you can do that because Clash basically gives you a way of running or simulating a signal cycle by cycle, and you can even interactively, like you can do it in I/O and then feed in the inputs and so on and so forth. As for performance, so in the simulator, we can very easily count cycles. It's cycle-accurate simulation. So we can see that most realistic 3-3 Sudoku boards are solved in less than 100 cycles. I don't know what your CPU can do in 100 cycles, but I'm pretty sure it can't solve a Sudoku problem. But there are some hard problems where it could take as many as thousands of cycles. So like that could, yeah. And then on a real hardware testing, so I took a Xilinx Atrix 7, which just by accident happens to be very similar to the one that Satnam was showing at his keynote. This is like a slightly smaller version of that. But with just the default settings, I didn't really try to find the fastest clock or anything. Just defaults to 100 megahertz, why not? It means that tens of microseconds is all it takes to solve a Sudoku problem. And as for the size of the circuit, so the proprietary Xilinx Vivado synthesis tool synthesizes it about 10 minutes, which is not too bad actually. It's like these tools can sometimes run for a very long time, even on these small boards. And the resulting circuit is about 9,000 logic cells, so which is about a third of this particular FPGA model for the 3-3 solver. Now, of course, the scaling is, in terms of size, is not so good because the whole point of this exercise is to use all the FPGA we can. So, we do all this propagation. Every single cycle, we propagate all immediate constraints because we have the structure that connects everything to everything. So for the 3-4 Sudoku problem, the logic cell usage shoots up to 25,000. So it kind of barely fits into the same FPGA. But for the, do you have time for just one more small tangent? Okay, so if you think about this stuff, right? Like if it fits in if it uses less than a third, that means you could fit 3 of this. And so when we pick a cell that we want to split on, there's absolutely no heuristic, when we are guessing, right? There's no heuristic on it. So what we could do is we could have 3 different ways, like maybe pick the first one, pick the second one, and pick the most middle, like the one that's just halfway between them. And we could race 3 solvers and then see which of them finds the solution first. So there is, like the future work to explore this, that given that it fits multiple times, how can we very nicely in the Haskell or in the Clash code express this idea of basically the hardware version of AMB? And yeah, that's basically it. So the takeaway message here is to check out Clash and use Clash because it allows you to write interesting hardware in a, I think, very nice way. Because note that all that stuff about monoids and monoidal actions and whatever, all this is really in the Clash code. We never had to that was not just to explore the solution space, right? This is what the final Clash code looks like, which is, I think, a real benefit to this approach. And yeah, and that's it. So yeah, thanks for.
Thank you for the talk. We have some time for questions now. There.
Yes, I have a general question about Clash. So So Clash on the surface is very similar to Haskell, right? You can say it's a subset of Haskell. So I wonder if you find it to be the case, because the target runtime is very different than the regular Haskell runtime. There's probably like no lazy evaluation in FPGA or whatever hardware it targets. So do you find it to be the case that a lot of the the idiomatic ways or good practice of writing Haskell are actually bad practices of writing Clash? It could lead to like very inefficient code, or if not incorrect code. Do you find that to be a problem?
Okay, so there are two parts to that. One is that situations like this one, like with recursion, where this is not valid Clash. Like this can't be synthesized into hardware because it's recursive and there's no finite circuit that corresponds to it, and then you have to solve that. The other situation is where, so this is single thing, right? So I said that, oh, we can just get it for almost free by comparing with 0. But if you think about what exactly is going on here, it means that for every cell, we're going to compute this split into 2 cells, right? But in a software version, you might think that, oh, this is very expensive, like this is needlessly expensive, because if I want to split my whole board, I can stop at the first cell that can be split, because because the whole point is that we want to find a guess, so just pick the first one, and then I don't need to look at the other cells. And if you look at it like that, you might say, oh, but then it's not really free. Actually, it's a very roundabout way of computing is single, because now I need to compute all this just to finally find that the bit count is 1. But in hardware, the cost model is different in that sense, because you have, like, if you have a branch, right? Like if you have a branch on, is this the first cell that can be split? That branch just corresponds to a multiplexer. But the parts are already going to be used for both branches. So if you have 81 such small circuits, and then you need to pick the first one, then it's for anything else that comes out of the 81 small circuits is for free, because you have to have those parts anyway. So in that sense, the cost model can be different.
Okay, so it does require you to think somewhat differently when you write Clash compared to.
Well, yes.
I wanted to expand on that a little bit, because I've spent quite a bit of time working in Clash, trying to convince a previous employer that we should use it for things. And the programming style that you use is very much not idiomatic everyday Haskell, but it's very idiomatic stream processing Haskell of applying pure functions to applicative streams that are potentially recursive. And once you start to internalize that and the mapping of that to hardware, it's so much nicer than any of the other languages that exist. Clash is decades ahead of using VHDL. There are notions that you can express in Clash that there is just no idea of in these other languages. Adam sort of touched on this the other day, that the languages that are used for designing these circuits are so backwards for the job that they are used for universally. And then you start working in Clash, it's night and day, just how expressive you can start to be and how you can build these reusable components and have a type system that's not completely bonkers. So yeah, you aren't writing idiomatic everyday Haskell, but the code that you do write is just so much better than the alternatives. All of the Haskell extensions all get used in Clash for the things that they should be used for, expressing things in the type system about the invariance of your system that you can't easily do in other languages. I feel like you can turn on.
I think that this kind of abstraction you can't really describe in Verilog or VHDL. When I think, oh, for any monoid, I know how to fold over my constraint structure. That's really, that's just not how you think. You can think about things.
You may have mentioned it earlier, but to get started in Clash, one needs an FPGA development kit. They're not typically sold in the usual to retail. So do you know like how much it costs and how difficult it is to obtain one?
To get started on this stuff, like $100 will get you everything you need. So I have like a Flappy Bird circuit that you can find on my So on my homepage, which is like yeah. So if you go to unsafe perform IO and follow some links, you can find some simple examples like Flappy Bird that plugs into VGA or HDMI screen depending on the board you have, and yeah, that would be like even not even $100.
Any other questions? So one at the back there.
Hi, Gergő. So my question might be a bit different to the others. So you said you wanted to raise multiple circuits in parallel as an idea. Do you know what the power draw difference then is?
Ooh, I have absolutely no idea.
I was just wondering, like, if these FPGAs, well, the FPGAs might be constant power draw in that, or you would
like
notice like, if you're just having
whether
like three times as much on there.
Use parts of it or don't use it, whether it makes a difference in power. I would think it does make a difference because if you don't use parts of it, the clocks don't even get connected.
Okay.
So,
All right, we're running a bit late, but since we have plenty of time in the 2-hour block, I want to ask one last question. It's not very specific to this work in particular, but more to the work using Clash in general. So you've been doing this for quite some time, and as we've heard here, we believe this is a great approach, and I think this is also a great way to describe something that's very low level, in my opinion, at a very nice level of abstraction. But I don't think it's really used a lot in practice. Why do you think that is? What are the barriers to adoption so that more people are using this in practice?
So I think a part of it is that the people who are doing this like professionally, the people who are actual chip designers, etc., like they don't necessarily come from a culture where the axes in which Clash shines are really acknowledged. So I think there's a big part of like there are cultures where if if you get the right output for the right input, the job is done. And I think it's very hard to sell on abstraction or on levels of abstraction or sell on tooling in those cultures. I think that's a big part of it.
Okay, let's thank the speaker again.